I'm Colin Brown.
I'm Mason Cipollini.
This is Lab 8 for OPTI 380 laser.
Under TA Lab New.
In Part A of this lab, we made observations of the modes of light when aligning the laser cavity. We started with a pre-aligned green laser where the gas tube was adjusted using the tip and tilt until the green light filled the tube and passed through to the iris. The system would then be adjusted without the tube to retroreflect the laser using a mirror. Then the gas tube would return and a Heaney would replace the green laser to finish alignment of the cavity. With the system properly aligned, many different modes can be observed with small turns of the gas tube tip and tilt. Additional modes could be seen by placing small fiber in the lasing cavity, disrupting the primary modes. In Part B of this lab, we used a Fabry-Perot interferometer to measure the cavity mode spacing. Our interferometer had a free spectral range of 1.5 GHz. This setup was the Heaney laser beam reflecting off of two mirrors and then into the interferometer. Using the iris on the interferometer, we centered the beam carefully before expanding the iris again. We then used the oscilloscope to measure the free spectral range in units of time, as well as the smaller separation of the individual mode. For the FSR, we obtained a value of 12.8 milliseconds, and for the mode spacing, a value of 5.1 milliseconds. Using these values, we calculated the delta mode of 598 MHz. Assuming a cavity of length 30 centimeters, we approximated a delta V mode of 500 MHz, which indicates our measurement is in the appropriate range.
In Part C, we used an optical spectrum analyzer to measure the central wavelength, mode width, and mode spacing of a helium neon laser and a laser diode. First, we enabled the alignment beam on the OSA, bouncing through a dogleg setup and into the laser cavity. We then turned on the helium neon laser and directed it into the input of the OSA. Using the software on the computer, we obtained a graph for the spectrum of the laser, from which we measured the half-peak width, central wavelength, and mode spacing. For the helium neon laser, we found a central wavelength of 632.85 nanometers, a mode width of 9 × 10 to the minus 3 nanometers, and no additional modes could be seen or measured. This process was repeated for the laser diode, of which we measured a central wavelength of 651.8 nanometers, a half-peak width of 2 × 10 to the minus 2 nanometers, and a mode spacing of 1.8 angstrom. In Part D, we used an electrical spectrum analyzer to measure the difference of the mode frequencies. We directed the beam of the helium neon laser onto the fast photodiode, which was connected directly to the ESA. We were unable to observe any peak using the first ESA, so we switched to the other one in the lab and were able to measure a primary peak of 888 MHz. We were unable to produce a secondary peak. Since the helium neon laser was the same as used in Part B, we can compare to our previously estimated value of the V mode, which was 500 MHz. These values are significantly different, and there are two possibilities. Either the ESA is inaccurate, or our Fabry-Perot reading is inaccurate, as well as our estimation of the lasing cavity length.